Okay, well, welcome back to our video series. Today we're going to be talking about Experiment 1, which is thin layer chromatography, also known as TLC. So anytime you hear an organic chemist talk about TLC, you need to know that they're talking about thin layer chromatography. The first thing that you might be asking is, what is chromatography? Chromatography historically actually is the separation of colored compounds. And so historically this was used as a way to take pigments from plants and actually separate them into their colored components. And so you can actually take a mixture of different pigments, so to speak, and actually separate them into their individual pure components. However, it has a more broader definition today. Today it's used to separate any mixture, complex mixture. So if you have a mixture that contains 2 or 3 organic compounds or even more, you can actually separate them using chromatography. And today we're going to talk about the special technique known as thin layer chromatography. And it's very important that you understand thin layer chromatography simply because you're going to be using it a lot as the semester goes on, as well as next semester in 256. So it's very important that we understand the basic concepts of thin layer chromatography. Not only does it allow us to separate mixtures, it also allows us to identify the components of a mixture. So not only can we take a complex mixture and separate it into its components, with thin layer chromatography we can actually identify what those components are by some values that I'm going to show you how to calculate here in just a moment. All chromatographic techniques, whether we're talking about thin layer chromatography or some of the other chromatographic techniques that we'll be learning about later this semester, require 2 things. You have to have a mobile phase, and the mobile phase for thin layer chromatography is a solvent, so some type of organic solvent, hexane, toluene, etc. There's a whole series of solvents that can actually be used for this. And you have to have a stationary phase. And for us, this is going to be silica gel, as we represent it as SiOX. Okay. So we're going to be using a mobile phase and a stationary phase. And it turns out that our stationary phase is a thin layer of silica gel placed on a substrate. And that substrate is either going to be plastic or aluminum. And we typically use aluminum-backed plates in our laboratories, but nonetheless you can use plastic or glass, but it turns out that the aluminum are particularly well suited for what it is that we're going to be using TLC for. Okay, so it turns out that the stationary phase, the silica gel, is actually coated on the substrate, in this case aluminum, in a very, very thin layer. And so you end up with what we call a TLC slide. And they're usually rectangular in shape, and I'm going to exaggerate the rectangle here just a little bit for ease of viewing. But in the lab you're going to find that there's an envelope full of these rectangular slides, as we call them. They're going to be somewhere around 6 centimeters in length, and they're going to be about 2.5 to 3 centimeters in width. And so you've got these little rectangles that are cut out. They've got the silica gel on the surface. There's an aluminum substrate on the back that holds that silica gel in place. And one of the first things that you're going to do when you go to get these TLC plates is you need to remember to wear gloves, because the oils in your hands will actually get on the TLC plate and interrupt your analysis. Okay? You also want to be very careful, since these are on thin aluminum foil. You don't want to bend them. If you bend them, you will break the stationary phase. It will crack and fall off and become unusable. And anytime you write on a TLC slide, make sure you make sure you use pencil, not an ink pen. Okay, so you can use pencil to write on the TLC slide. You must wear gloves, and don't bend the slide any more than you have to. Okay? So what we do with the TLC slide is you will come in and you will measure about 1 centimeter up from the bottom, and you will draw a very light line with a pencil. This line is known as the origin. This is where everything begins from, and you need to be up about 1 centimeter on the slide. Then what you will do is you will place spots of your compounds of interest And I'm going to use black for one spot. I use green for a third spot just to show that there are different compounds. And then blue for a third spot. And typically on a 2.5 centimeter slide, you can get about 3 spots on a single TLC slide. Your TA is going to show you the technique of spotting. Spotting is actually an art, and it takes a little while to get used to it. You don't want spots that are too big, and you don't want spots that are too small. And so it takes a little bit of practice, and your TA will actually teach you how to do this. Okay? So once you've applied your spots onto your TLC slide, you're going to place it into a jar that we call a TLC development chamber. Okay? Go ahead and erase this. So we've got our spots on there. We've allowed the solvent to air dry, so the spots are adhered to the slide. You then place this into a jar that has a lid on it. Okay? And that jar is going to have inside of it some solvent, our mobile phase. And it's very important that the mobile phase not touch those spots that you made. It has to be below the origin line. So make sure that you don't have a jar that's just completely full of solvent. You need a very small amount of solvent in the jar. Once you place the TLC slide in the jar with solvent, that solvent is going to start to creep up that TLC slide by capillary action. So the solvent will actually flow in this direction. Once the solvent has made it to about anywhere from about 0.5 centimeter to 1 centimeter to the top, we pull the slide out of the jar and actually mark how far the solvent's gone. So I'm going to just arbitrarily mark there as if the solvent has gone there. What you will notice, once you remove the TLC slide from the jar, you're going to let it air dry. You're then going to put the TLC slide in a UV box. We've got a UV lamp inside this box that you can, your TA will show you how to use. And what happens then is you'll be able to visualize your spots. You'll be able to see where they've moved to. Okay? And so perhaps after visualization, we notice that the black spot has moved to about there. Maybe the green spot has moved all the way up here. And perhaps the blue spot is somewhere in between. So we'll just arbitrarily put it here. Okay? And what you can notice is that the spots move different distances. And so we can define what's known as an RF value, which is a constant that allows us to define or identify particular components if we have the proper standards to do this. RF is defined as the distance that the spot traveled, and I'm going to call that DC for component, over the distance that the solvent has traveled. And a good way to do this, of course, is just to simply use a simple ruler. And usually we measure these either in centimeters or millimeters. I prefer that you use millimeters simply because you can get more accurate measurements because you've got more little marks on your ruler. So what you would do is you would measure from the origin the distance that the spot travels. So in this case, we're talking about the black spot. So you would take that distance, which we're going to call DC, and you would divide that by the distance that the solvent travels from the origin to the top of the solvent line that you drew when you pulled the slide out of the solvent chamber. So this is DS. Notice that this is a unitless value. And we typically report these to just 2 decimal points. So for example, this looks like it went up about 1/3 of the way. So you would report the RF for the black spot as 1/3. You can put that into your calculator, of course, get 0.33. Don't go out to 5 decimal places. We can only go out to about 2 accurately. So the RF for this particular compound, this black spot, would have a RF value of 0.33. It's very important that you note you cannot have an RF value greater than 1. Okay, since they are ratios, your spot cannot travel any further than the solvent front. It's just impossible. So if you end up with a value that is greater than 1, you've put the solvent in the wrong place. So you've just changed these around. So DS is on top, DC is on the bottom. You need to make sure that you go back. So anytime you get a value of greater than 1, you know you've done some improper math. Okay? So, how does it work? This works because the silica gel substrate is polar. And our organic solvent is a, relatively speaking, nonpolar mobile phase. So we have these two phases. We've got a polar phase and we have a nonpolar phase. And you can recall back from general chemistry that you learned that like dissolves like. Polar things like to associate or dissolve in polar solvents, whereas nonpolar things like to dissolve in nonpolar compounds. So we've set this up to where we have a polar phase and a nonpolar phase. And if a compound is very polar, it's going to want to stick to the solid support. It's not going to want to travel with the mobile phase. However, if we have a compound that is very nonpolar, it's going to want to stay in the liquid mobile phase and travel with it and not spend so much time on the solid support. And that's how we end up separating these compounds based on polarity. So highly polar things will not move very far and have very small RF values, whereas nonpolar molecules will actually travel a good bit up the slide and have RF values closer to 1. So let's look at an example